Afternoon, thank you for coming. So today I'm going to present on a sequence analysis approach to understand migration and human capital pathways. And then my colleague, so Chris from the University of Liverpool and also Alex are going to present on a different topic regarding spatial processes and spatial data and different approaches. So we move on. So just to give you a bit of a context, so I'm going to be focusing on a specific approach to understand spatial processes. And that is essentially because it's quite challenging when you look at spatial processes over time. So one of the complexities is that you need to manipulate large, comprehensive longitudinal data sets. So, and that means a lot of different observations over an extended period of time. And it's becoming more common as data become available. Another key challenge that we face is conceptual approaches to look at these processes over time. There are very little, so most approaches tend to be static, so which means they are cross-sectional. And then the other difficulty that we face is that we want to capture multiple dimensions of spatial processes. That is, so the incidence, so how many times a particular process takes place or happened. The duration, so the time a process lasts or a change may last. So the timing, the time at which it occurred. And the sequence, so the chronological order of different processes or changes. Alex? So to give you further context, I'm going to be focusing on migration. Why migration? Well, migration is a significant process. If we look at it from the regional perspective, we see that migration redistribute labor, skills to places where it is needed. But also, if we look at migration from an individual point of view, it also enhances human development and individual development. So migration enables people to take up opportunities in different places, okay, and realize their aspirations. Although there is a lot of studies, a lot of literature on migration, there are still some key relevant policy questions that remain to be addressed in a proper manner if we look at so long sequences of data. So I have listed a couple here. So why, for example, or how long do migrants stay in a place? We tend to understand migration as a permanent decision, a permanent move. But if you look at young people, they tend to move to acquire education, but then they usually leave or move on. So they don't stay in a place for much longer than 3 or 4 years. Then we are also interested in move up and down the urban hierarchy. So people move for different reasons, up and down. And why is that important? Because, as I said, migration brings skills and labor, so it has an impact on the local labor market. Then there is also a question on return mobility. And usually when we look at non-metropolitan areas, they tend to experience large flows of young people leaving non-metropolitan areas to major cities and urban areas. So there is really a question, a policy question, how many people go back of those who left, and how many of those apply the skills in non-metropolitan areas. Then there is the question also what activities they are looking for when they leave. So are they looking for university education? Are they looking for vocational education? Are they just looking for a bigger labor market when they can apply or have access to more specialized services or occupations? And then, so it's about the impact of migration on individual careers and earning capacities. So today I'm going to be focusing on that a little bit. So I'm going to be talking about findings of a project that I was working before moving to Liverpool at the University of Queensland in Australia. So in August, so I spent 3 years working on this project, looking at migration from non-metropolitan areas and the impact that that has on non-metropolitan labor markets, but also on individuals that left non-metropolitan areas. So it was a project in collaboration with different government agencies in Australia and different educational institutions. So the focus of the project was, as I said, focusing on the impacts of migration. So what we've done, so we were focusing on non-metropolitan young people living in non-metropolitan areas. And as you may know, so the migration of young people from non-metropolitan areas to urban areas or major cities is a long-standing demographic process or phenomenon. So if you look at industrialized countries or emerging economies, what you tend to see is continuous outflow of young people from non-metropolitan areas into urban areas. And that is because they are looking for education, they are looking for employment, they are looking for a more vibrant lifestyle. So the purpose, so the research, one of the purpose, so was looking at the salary returns to migration of young people. So because we know that young people are the most mobile if you look across the age spectrum. So what we did here, so we work with a longitudinal data set of young people. So they enter the survey when they are 15, and they are surveyed every year for 10 years until the age of 25. And that is the longitudinal survey of Australian youth. Okay, so we look at people living non-metropolitan areas. So what you are seeing here is, so on the x-axis, so it's the number of years before migration and the number of years after migration. And here on the y-axis, you have the mean salary per hour. Okay, so what you see, because here we were focusing on looking at the returns, the salary returns of migration for non-metropolitan young people. So what we tend to see is that after they migrate from a non-metropolitan area, what they tend to experience is a significant reduction of about 50% of their salary. And as they stayed in metropolitan areas, what they experience is a rapid increase until about year 3, they reach the same level of salary that they had before the move. But then it increases even more in subsequent years. So on the last bit where we see a decline, that can be explained because of the number of observations that we had, so for 9 to 10 years after migration, okay? So and then the question was really, so what happens here that increases the salary capacity of people? So what are the pathways that people follow? So talking about educational and employment pathways. So the challenge here was to identify representative educational and employment pathways. Okay, so and then I started looking at different approaches, how we could build or define sequences or trajectories of people, looking at educational and employment statuses. So I came across sequence analysis, which originated in molecular biology for the analysis of DNA. So essentially, this analysis involves two processes or two steps. One, so let me go a step back and say, so what we were trying to do is to form cluster of different sequences. And we couldn't apply so the traditional cluster methods, cluster analysis methods. And that is because they are built to work with continuous data, right? And looking at cross-sectional data sets. So but what we had here was a longitudinal data set of categorical variables. Okay? So the first step, as you may know, for cluster analysis is you need to get an estimate of the distance of the difference between different points, so different observations. So and in sequence analysis, we do that by using optimal matching techniques. So and what it does is measure the similarity or dissimilarity between individual sequences. So and the way that it does that, so it estimates the minimal cost of transforming one sequence into another. And for that, it uses two operators. So one is called indel cost, which is the deletion or insertion of one status. And then the other, so and that is by definition or by default one, okay? And then there is substitution cost. So just to explain a little bit here. So let's say we have three statuses. So S, school, B, vocational education, U, university education. So, and in that case, so what you see here is that the cost of transitioning from school into vocational education is much larger than transitioning into university education. And that is because these substitution costs are based on transition costs or transition probabilities. So if we look at the transition rates or transition probabilities, we can see that the probability of transitioning from school into university is greater than the probability transitioning from school into vocational education. Okay, so based on those two costs, we built our estimation of optimal matching. So, and just to give you a further example on this. So let's say we have 4 different individuals. So, and we have some observations at year 17, 18, 19, 20. And we see that their statuses at different years are, for example, school, everyone, then they have different combinations on vocational education and university. Okay, so, and if we wanna translate or estimate the cost or the distance between two sequences, so let's say we wanna transform sequence 1 into sequence 2. So it would be that sequence into that sequence. So what we do, we substitute one of the statuses here. So vocational by university education. So and we would get a cost of 1.91, which is the cost that we have here. Okay? So, and for example, let's say we want to transform sequence 4 into sequence 2. So the only thing that we want to do and what is the minimal cost is if we delete this status and we transform then sequence 4 into sequence 3. So then having built these metrics on the different costs, so what we do is then we apply a cluster technique, which is called around methoid cluster algorithm. So that cluster similar sequences based on the estimated cost computed during the optimal matching process. Okay, so it's a similar two-step process as you would do for a normal standard cluster analysis. So we did this looking at employment and educational sequences. So what you have here, for example, so we identify 5 different clusters. We use statuses across these different dimensions, so education and employment. So looking at whether if someone was active or inactive at the school, in vocational education, university, full-time employment, part-time employment, or unemployed. So and the different colors represent each of these statuses. So for example, here we look at the first cluster at age 15, that status. So if we look at that, at the legend, so we can see that it means school. So at year 15, everyone was at the school. And then as you go, so you can see, for example, so this is the number of people in this cluster. So and each line of those represents one individual sequence. So and if you look, for example, at individual 1, so you see that that person moved from from school into university education and then ends up in full-time employment. So when we start looking across the sequences and across the clusters, so what we see is that a particular trend of different pathways. So and we identify these different pathways. So the classical pathway, which is comprised of 1,000 and over 200 people. So the representative sequence here is going from school into university and ending up in full-time employment by the age of 25. Okay, so and we have another one, which is the spread sequence, which is from school into full-time employment, unstable sequence from school into part-time employment, the bridge sequence from school into vocational education, full-time employment, and then the extended education sequence, so people that remain in university education. And if you look, so compared to the classical sequence, so all the other sequences leads to much lower salary, okay? So a salary disadvantage, if you want to say it. So then we started looking at how, so the representative path or how the proportion of people that migrated from a non-metropolitan area, so what was the most common sequence that they followed. So the larger proportion of people tend to follow a classical sequence, which is from school into university and into full-time work, and an express sequence, which is from school directly into full-time employment. When we compare, so the old ratio of those people, so non-metropolitan migrants, with those staying in non-metropolitan areas, so we tend to see that those that live metropolitan areas tend to have a higher rate of transition through a classical and an extended education sequence. But not so if we compare those sequences with those of metropolitan stayers. So essentially what that means is that they are sitting in a sort of a middle ground. So they do better than people that stayed, but be worse than people that are already in metropolitan areas, okay? So then the question was, so further analysis on this, and then we look at whether if these pathways really matter. So if we control for any other characteristics, personal, family, educational, employment, and so on, so different characteristics, so whether following different pathways would have an impact on salaries at the age of 25. So because we are talking on skewed distributions when we look at salaries, so we apply a quantile regression at the median. So what we see is that when people sort of deviate from a classical pathway, which is the control category here, so and particularly if they transition through an unstable pathway or extended education pathway, so they tend to achieve much lower salaries at the age of 25. So for unstable pathway, that kind of makes sense because people tend to do worse. They tend to do transition from school into inactivity, but then also into part-time work. For the time period that we see these transitions, we don't see that they get full-time employment at any point. For extended education, that is a bit more difficult. So we started looking into the data and exploring a bit further. And what we saw is that a lot of those people, they stay on for a master, for a postgrad, for postgrad education. So, and most people were engaged in part-time work. So we were expecting, and if we had more data, we would expect that then thereafter they would have an increase in salaries. So we compare those outcomes to non-metropolitan stayers and metropolitan stayers. I'm not going to go on explaining that. So we found almost the same results. So and to conclude, so The research shows that young people migrating from non-metropolitan areas in the transition from school to work leads to higher salaries than non-metropolitan stayers. So people that stay tend to earn a lot lower, but similar salaries compared to people that were already in metropolitan areas. Then what we also see is that salary returns, they are not immediate. They take about 3 years. And then we also see that people that deviate from a classical pathway tend to earn lower salaries, particularly, as I said, if they transition through an unstable or an extended education pathway. Well, just one remark here is that, so it's important to acknowledge that we are looking at salaries at the age of 25, so we could expect differences to converge if we look further into their lives. So I think I'm going to park it there and hand it over to Chris.
Right. Just actually to take a bit of a step back, obviously this session is about turning spatial data into information. So Francisco's talked about a dynamic spatial process. I'm going to talk in a kind of more general way about a conceptual part of working with spatial data. As a bit of promotion, I'm just going to point out an address there for the Centre for Spatial Demographics Research, of which I'm director. It provides some background on an area of strength at Liverpool, which is to say working with spatial data in a kind of social and economic context. So if you want to have a look at that sometime, do. We're adding resources like GIS learning resources and things like that. So you might want to have a look at that if you're interested in this general theme. But what I want to talk to you about specifically today is scale in relation to spatial analysis. It's a bit of a different approach to what Francisco's taken. Scale is relevant to anybody working with spatial data. You cannot ignore it. Whether you're working with aggregate data like released from the census or individual level data, it is relevant to you. And what I mean by scale in this context is not map scale, like 1 to 20,000 or whatever, but it's like the definition at the top there. It's about the size or extent of a process, a phenomenon, or an investigation. And I'll explain what I mean by that later on. But you could be talking about the scale of spatial concentrations of some population group, for example. So we're not talking about map scale. As I've already said, any analysis using spatial data depends on the scale of your observations or the scale of the process that you're looking at. And again, that will become a bit clearer in the next few minutes. I guess most of you have probably heard of the modifiable aerial unit problem. It's relevant if you're talking about scale. What it means is if you work with area data of any kind, like enumeration districts, output areas, districts, counties, countries, whatever, your results depend on the size and shape of zones that you are using in your analysis. They are modifiable, which basically means it's rare that you get an objective definition of an area. You can change the boundaries a little bit, report your data for different areas, and you will get slightly different results. So that's relevant as well. My specific focus is going to be on, as I've got here, residential segregation and spatial inequalities. It's one area of many in which scale is important, and it's a good way of kind of illustrating some of the key issues when we think about scale in spatial analysis. I'm going to look briefly at some measures, including something called a variogram. I doubt if anybody here has heard of variograms, or if you have, it's probably in a vague way. They're not widely used in social science contexts. I'll illustrate their use through an application looking at population change in England and Wales between 2001 and 2011, using census data for those periods. So another way of thinking about scale is to actually look at some maps like these. So on the left-hand side, we've got limiting long-term illness. The reds are low rates of limiting long-term illness, and the blues are high rates of limiting long-term illness. The equivalent on the right-hand side is for the percentage of social rented households. These are in census wards. So if you look at the map on the left, you can see kind of quite a large scale variation. We've got lower rates generally in the south and east, and higher rates particularly in urban areas of the north. We've got a slightly different pattern when we look at social rented households, with places like London, Birmingham, Manchester, Liverpool popping out with high rates of social rented households. So the scale of the process in these two cases is really different. What that means is the choice of zones that you use to analyse either of those characteristics has a different impact. If something varies a lot over small areas, the choice of zones is really important. So if change between one neighbourhood and another is really high, the choice of zones you use is really important. If large areas are really similar, it doesn't really matter what zones you use, you'll get the same sorts of results. So if we're thinking about these sorts of effects, if we're thinking about the way that our results might change, there are different ways that we can explore that. We could change the zone size, so we could conduct some kind of analysis, whatever it is, using output areas, or bigger zones like lower layer super output areas, or wards, or districts. So we could change the zones we use, reconduct the analysis, and see what kind of impact it has on the results. We could also change the neighbourhood size. So what I mean by that, let's say we're looking at clustering between areas. So we take each area in turn and we look at the neighbouring areas. We could look at the nearest 25 areas or the nearest 50 areas or all of the neighbouring areas within 1 kilometre, 2 kilometres, 3 kilometres, whatever. And we can vary that neighbourhood size. That will change the results of our analysis of in this case, clustering. Another thing we could do, which I'll come to later, is to look at the differences between observations, say unemployment percentages, between places separated by different ranges of distances. And hopefully I'll make it clear what I mean by that in a little bit. Now, if we're interested in things like segregation or inequalities, one common measure is the index of dissimilarity. I've got a few basic equations here, but this one's pretty straightforward. So little x is the proportion of people in some subgroup. Like, let's say it's employed people. Big X is the total unemployed people in our study area. And then the other side of the equation, the Y's, might be the rest of the population. So that might be the unemployed in an area over the total unemployed. So it's a measure of the spread of population groups across the study area. And if it's a value close to 1, it means that there's an uneven spread. So unemployed people tend to live in one set of areas and employed people tend to live in another set of areas. If it's close to 0, they're pretty equally spread. Every zone's got similar proportions of the two groups. So using that index, this is measuring religious segregation in Northern Ireland. This is an area that I've worked on quite a lot in the past. Now, we could use lots of different zones. At the top, we've got output areas. We've got, I think there are wards in the middle, and then districts at the bottom. So we could take our populations of, in this case, Protestants and Catholics by religion. For each of these areas, we could use that statistic and we would get slightly different results. In fact, if you see what I've got here, I've got the same data, but they're reallocated at an individual level to different sets of zones. So they're exactly the same underlying data. This is them being assigned to enumeration district boundaries. So this is a kind of pre-census geography. This is output areas and then 2 different sets of wards. So exactly the same data. You'll see the figures for the 2 smaller sets of zones, which is what these are much bigger than for the larger sets of zones, which is wards. So as we classically find, segregation is smaller if we use larger zones. So segregation is a social construct, but it depends entirely on the set of data that we use. We will likely see higher rates of segregation if we use smaller zones, because smaller zones are more likely to be homogeneous and to therefore differentiate population subgroups. We can use other measures of spatial organisation. This is Moran's eye. It's a measure of the correlation between values at a location and at neighbouring locations. So if you get a large value, it means that values are close to their neighbours. If you get a small value or a negative value, it means that neighbouring values tend to be dissimilar to one another. So values that are positive and large, you get clustering. Values that are negative, neighbouring values tend to be dissimilar to one another. So we can use this statistic to measure clustering. We can use different forms of zones, and we'll get potentially different results. We could also use something like a variogram. Given the lack of time, I'm not going to go through this definition that's written down here. I've got some illustrative slides that will make it clearer what I'm talking about. But essentially what a variogram is it's a measure of data values and similar data values separated by a range of different distances. So if you took unemployment at each location and calculated the average difference to unemployment at locations between 0 and 10 kilometres away, so you've got an average then of the difference between any unemployment observation separated by that range of distances, then you increase the distance range and you do the same thing, and you end up with a set of average differences for distance ranges. And I'll give you an example in a minute. If you plot those differences against distances, what you'll often find with true geographical phenomena is a pattern like this, where you get small differences at smaller distances, and as the distances get bigger, the differences get larger. And that's natural with any geographical process that clusters, and most socioeconomic processes do tend to cluster. You tend to get neighbouring values being more similar than values further apart. You can fit a model to that, like what we've got illustrated here, and it tells you something about the scale of the process, the size of the concentration, if you like, of the population group. So it gives you, for example, this piece of information here is analogous to the variance. So on the y-axis is analogous to the variance. If you get a bigger value on this axis, you've got more variation in the thing you're interested in. This value, so on this axis, tells you about the scale of variation. So if you have a large variance and a large what's called range, it indicates you've got really big regional trends, really big differences between large regions. If the range is small, it indicates clustering over very fine scales. So it gives us one composite measure of the nature of spatial variation in whatever we're interested in. This is a synthetic surface. On the left-hand side, it's got a small range, so that looks really noisy. Something like limiting long-term illness is quite noisy relative to other variables. You get big differences between neighbouring areas. On the right-hand side is a big range. So this is something with large regional variation. So something like ethnicity, for example, is the case in England and Wales. So taking an example, we're looking at England and Wales. We're looking at census data from 2001 and 2011. We're looking at a range of variables, social, economic and demographic, so ranging from age through to ethnicity through to housing tenure. And what we're interested in is how their spatial arrangement has changed, how clustering or concentration of these variables has changed across the two censuses. And we're going to use all of the three sets of statistics I've talked about. The index of dissimilarity, a measure of unevenness, a measure of clustering, which is Moran's eye, and then this thing called the variogram that I've just spent a little bit of time talking about. So those are the variables. Not going to spend too much time on that, but they're a sort of fairly coarse set of variables, as I said, ranging from age through to ethnicity, housing tenure, car and van ownership, national socioeconomic statistics classification, and limiting long-term illness. This is the index of dissimilarity. So if it's close to 1, it indicates greater unevenness, so bigger differences between areas. If it's close to 0, it indicates that areas tend to be quite similar. So the areas in red tend to have more evenness. Those in blue tend to have greater unevenness. And we kind of expect what we see. If we see this coarse measure of ethnicity, it indicates a high level of unevenness relative to other variables. And that's simply because the largest feature of ethnic geographies in the UK are obviously urban as against rural areas. So we'd expect that. Also, social rented households as against anything else is quite high. We expect that because we have areas where social rented households are concentrated. With age, we wouldn't expect there to be any particular geography, not in the same way as there are for socioeconomic variables. So you tend to get a smaller value. We can use a measure of clustering, and I've already said when it's close to 0, it indicates dissimilarity. When it's closer to 1 or it's a bigger value, it indicates more clustering. This is a transform of the standard basic data. I'm not going to talk about it in any detail, but it shows clustering, and this is not in a kind of process sense. It's merely in a statistical sense in terms of ethnicity, but low levels of clustering in terms of age. And I could spend ages talking about these results, but I don't have time. But it's just a way of summarizing. The left-hand column, the first column, is looking at clustering over a small neighborhood. The next column is increasing the size of the neighborhood, and the amount of clustering that's measured changes. And if you do that for lots of neighborhoods, you can characterize the overall scale of variation in the property that you're interested in. Now, these are variograms. For top, the population which belongs to one of the white groups is against the population that belongs to a non-white group. The middle, owner-occupied and private rented households contrasted with social rented households. And then at the bottom, those people with a limiting long-term illness, so something which prevents them living a normal day-to-day life in some way, shape or form, as against those who don't have a limiting long-term illness. And you've got two of them, one for 2001 and one for 2011. In the top case, we've got the top one is for 2001, the bottom one is for 2011. So it's dropped, so the variance has decreased. That means the overall difference between areas in terms of their ethnicity reduced between 2001 and 2011. The ranges, which indicate kind of differences between urban and rural areas, are almost the same. They're very, very similar. So the overall pattern of ethnic geographies in England and Wales is similar, but the differences between regions have decreased. In terms of housing tenure, The top one is 2001 again, and the bottom one's 2011. Again, the variance has decreased, so there are differences between places, probably as a result of things like the right to buy scheme, which means that we've got a mixture of tenures in areas that were formerly social rented predominantly. So again, there's a reduction in regional differences. In terms of limiting long-term illness, we've got a different pattern. Variance has increased, so the difference between areas has increased over this time period. So showing the same three plots again, this is a map on the right-hand side of ethnicity using this very simple categorization in 2011, and you can see that the classic urban-rural differences with places like Birmingham, London, Manchester coming out. But as I said, the variograms show similar spatial structure as you'd expect. You haven't got a massive change between those two time periods, but the differences between regions of England and Wales have reduced over this time period. But the key thing to stress is that we've got a composite measure that we can plot that tells us about the overall spatial characteristics of this property. And that's really important for a whole host of reasons. This is the equivalent for social rented as against other households. This is just zooming in on a more local area. But again, we've got a measure that tells us about the structure and how it changes. And then again, for limiting long-term illness, where the contrast between neighbouring areas has actually increased. So inequalities in terms of self-reported health have grown over this time period. So to recap, as we'd expect, demographic variables like age don't tend to be strongly clustered, at least not compared to socio-economic variables. Most population characteristics have changed in a very distinct way over the period of 2001 to 2011 in the sense that differences between areas have reduced. So in some senses, spatial inequalities have actually reduced over the 10 years between 2001 and 2011. Local areas tended to have become more similar over this time period, but differences between regions tended to have decreased in terms of most variables. So what we're seeing, like I've said, is a reduction in differences which might suggest a reduction in spatial inequalities over this time period. And the variogram is a really useful way of characterizing things. But the variograms will be different if I hadn't used output areas. If I'd used lower layer super output areas or wards, I would get a different structure. So all of my results are entirely dependent on those choices. So scale, whichever area you're working is relevant. If you're working on segregation or diversity or deprivation, so if you're measuring deprivation, if you're looking at spatial inequalities, the size of zones you use is crucial. It can completely change your results. The direction of change between one time period and another can change. The direction of change can be the opposite if you use different sets of zones. So you have to be aware of this if you're using data. Don't just go and use wards or output areas and assume it will all be okay, because it might not be. You need to know something about the characteristics of the property and how it relates to the size of zones. If you're doing any kind of regression modelling, even if it's using individual level data, if you're using a multi-level model, the levels that you use will affect the results that you get. If the areas that you're using as part of your nested hierarchy are too large, you're kind of removing any variation in the population feature that you're looking at, and you'll get different results than if you use smaller areas. If you're doing some kind of area classification, like a Geo Demographics classification, the kind of stuff that Alex does, the results will depend on the size of the zones that you use. So though the methods that I've talked about are quite specific, the context that I've looked at is quite specific, it's just hopefully getting across the fact that there are some useful tools for measuring scale of variation in population characteristics in this case, and you really do need to know something about that if you are working with any kind of spatial data. So with that, I'll hand over to Alex.
My name's Alex Singleton. Like the other two speakers, I'm also at the University of Liverpool. I'm director of something called the Consumer Data Research Centre, which is one of the ESRC's big data infrastructure centres. So we house lots of consumer data and related data, which might be of interest to you in your sort of research. But I'm not going to talk about that today. But what I'm going to talk about today is something called reproducibility. This is essentially what happens when I was a PhD student. So I'm a geographer, so I'm building maps. I'd use a tool like ArcGIS, create some maps, not very exciting maps. I was doing a lot of statistical analysis, using something called a SAS. I don't know if anyone come across SAS. It's not a good tool. So SAS looks a bit like this. It's a very boring interface. So two separate things going on here. It's not very good for graphs. So you fire up Excel, you've got some CSVs out of SAS, you put them into Excel. You've got Excel open, you're producing graphs like this, getting all of that together, copying and pasting it into a Word document, and then you've called it, version 1, chapter 1, version 1. You're very pleased with yourself. And then you realise when you take it to your supervisor, it's appalling, and you've done it all wrong. You've got to do it again, so you end up with version 2. And this progresses, and you know, if you're like me, up to about version 16 by the time it's anywhere near sort of acceptable. You've then gone at version 17, final, final, version 2, this is the final one, etc., etc. So essentially, I used to end up as a PhD student with directories full of files. I had no idea which data files had created which graphs. I had no idea what data had gone into models, because there wasn't really any sort of chronology of how these things would be created. I didn't know which files from the Excel document were within these sort of Word directories. And then your supervisor would say, do you know what, I think all these chapters are in the wrong order, let's just reshuffle around. It was just complete chaos. And I went through this with my PhD, and obviously, you know, now an academic, it sort of worked out in the end, but it was very, very difficult. And I always thought there must be, you know, a better sort of workflow. And in part, you know, tools have developed over time. I sort of finished my PhD in 2007, so things have evolved since that time. And really, that's what this reproducibility discussion's around. There's other very good reasons for doing it. This is an example from the economic literature of a paper which is quite famous because it was one of the papers which actually made the case for why austerity policies should be introduced in economies with certain characteristics. This was produced some sort of economic analysis in an Excel document. It was quite sort of a lengthy table of countries, series of attributes, some models fitted and some results presented. Some grad students at another institution in the US weren't sure about this model. And actually what they did was they emailed the author and said, could we have the data? And he was like, yep, no worries. Transpires in this paper, which is quite well cited and also used by governments, but actually when he'd copied the formula down the Excel column, he'd missed out about 7 or 8 countries at the base of this column. And in fact, if you added those in, that was an error, and completely changed the results in the opposite direction. So it was all unfounded. And obviously the implications for austerity, as we know, are quite severe across the globe. So that's quite interesting. If it'd been more reproducible and a bit more transparent, we'd perhaps been able to sort of spot these errors earlier. Another example is what was referred to in the popular press as Climategate, referred to an email hack on climate research units at University of East Anglia. Series of email discussions were essentially hacked and made public. And then there was some debate about some of the claims that the scientists were making about climate change on the basis of this. And there was a call for them to put their models into the open. Now, they couldn't do that, and the reason they couldn't do that is the inputs to those models were proprietary. And that would mean if they were proprietary, you wouldn't be able to put that data into the public domain. So they weren't able to make those models open and transparent, which again perpetuates the idea that they're trying to hide something, but actually it's just license restrictions. This is another example from Nature. There's quite a lot of organisations now interested in reproducibility. They'll take published research, take the data, fit the same models, hopefully get the same results. And what this is saying is actually that's not the case at all. And in fact, most of these scientific studies that they actually looked at weren't reproducible. And this is sort of this colour gradation sort of indicates like how unreproducible they were and how different the results were that the people who were testing them got. So reproducible research is really, as I said, it's about sort of a pipeline from taking data, methods, and looking at results and presenting findings and conclusions in a way where at sort of all stages in this process, it's reasonably transparent and reproducible. There's a series of reasons why you might want to do it. First one, you might want to mitigate errors. So if you put your sort of preliminary work out into the public domain, someone looks at it and says, oh, look, you know, you've done this, this, and this wrong, and you might get some feedback on that. I've put code out in the public domain that I've developed for different things. People have spotted errors in that, corrected it, and then, you know, the final result's actually okay. I think there's a general feeling that if you can put your stuff in the public domain, that people can treat the full suite from the data through to the results. You could give the public sort of greater reassurance. So in the context of the climatic email hack, yes, we're doing good science. Public's reassured that this is something that's happening. There's an ethical point that public-funded research should be made public. You know, we're paid as academics by the public purse, arguably some commercial and sort of student incomes, but essentially it's a public good, and therefore, you know, the work that we create, we should have out in the public domain for the public to consume without cost. Impact benefits: if you're an academic, you're expected that your research will be used by the general public, by other stakeholders such as the public sector or the commercial sector, and there'll be some impact of the work that you've done. And I would argue that doing things openly in a reproducible way can really enhance impact. And I've got a couple of examples of that from my own work at the end. So the process, I'm just going to check the time, the process from sort of data, method, results, and then the final presentation. I've not got a lot of time to go through these in detail, but in terms of the types of data which are reproducible, there's something called open data, which essentially means that whoever collected the data was willing to put it in the public domain with licenses which enable it to be reused, repackaged, and redistributed without cost. And you don't necessarily even have to tell the source of the provider of the data that you've done that. The idea is that there would be, if it was a government data set, there would be some economic benefit or some social benefit of that data being in the public domain. Someone might have used it to create, you know, an app which finds a safer route home, you know, a more sort of monitor lifestyles and sort of more healthy lifestyles and those kind of things. So just one example of where you can get lots of open data. The Consumer Data Research Centre, as I mentioned, I was a director of. We've got a data portal there. Most spatial data in the UK, which is available at quite a sort of disaggregate level, the sort of stuff that Chris was talking about, we've repackaged in a way which should make it very easy to use there, and that covers all sorts of different things from census data like Chris talked about, right through to broadband speeds or survey data, plus a whole host of other things. There's a catalogue of all our data holdings. So that's one example of open data, and there's lots of other open data portals. Methods, all those things I talked about at the start, my first slide, I don't use any of those anymore. And the reason I don't use any of those anymore is I learned R and Python, and what they are statistical programming languages, and pretty much any functionality in any software has been written in these two tools. They're not actually that difficult to get into. There's a little bit of a hurdle, but I mean, we even teach it to our sort of second year undergraduate geographers who've got no computational science background particularly, and you know, they seem to find it okay. With those are all free and open source software, so a community of people develop them, and the nice thing about them is you type your code in a linear fashion, and that means it's completely reproducible, so you know exactly what data you've used, you know what methods you've used, you know what your changes are, and so on. The way in which that can be integrated into a sort of document, and you can replace things like Word and all these different packages. There are software called, there's a piece of software called RStudio, and there's something else called Jupyter Notebooks for Python. And what they enable you to do is there's a series of ways in which you can embed some of these code that you might write, say to build a graph or to join a table or build a map, with sort of narrative descriptions of your interpretation of those sort of data assets. And you can render from those PDFs or Word documents or whatever you want. So it's a way of joining code for actually doing analysis using data and sort of presenting it in a way where it's embedded with your sort of discussion and narrative around those assets. This cat here is actually not a cat, it's an octocat, half cat, half octopus, is the logo for something called GitHub. GitHub is a code sharing repository. Now, principally, that was used by people, for example, who might be writing additional functionality in R or Python or any software. It's open source, and you commit it to a GitHub repository. Other people sort of use that and bring the code down. They might make changes and put it back, and it's a central repository for sharing code. But increasingly, people are using it for academic work as well. So my colleagues and I will write papers using a system such as this, and we'll actually host a paper on GitHub. So we'll actually keep all our code and the sort of narrative on GitHub. You can make those open or closed, so you don't have to put them into the public domain. And it's quite a nice way of sort of managing that process. And the final sort of stage, if you like, if you get to that stage, is you might be creating publications. There's obviously a range of different ways in which you can publish openly, from putting things out into your institutional repositories or your own websites through to journals. Typically, if you've got funding from one of the research councils, you'll be able to access funds within your institution to publish what they call gold open access. This is a shameless plug for my own journal, which I'm editor of, called Regional Studies, Regional Science. That's an open access journal. So essentially any content which goes into our journal pays a very small fee, and that means that anybody can access it. So you don't have to be a university or with a university account. Now, I mentioned one other thing earlier on about impact. And actually, if I'm honest, I think this is probably one of the key benefits for early career researchers about putting your stuff out into the public domain, that as many people as possible can access it without passwords. This was a piece of work I published in another open access journal called Geo. As Chris mentioned, I do work on Geo Demographics, which essentially take lots of data about places and look for those places which share similar characteristics. And those similar characteristics are, in this case, just for the extent of London, and you colour all the areas in London into these different groups. And that's basically a geodemographic of London. Now, that again, so that it was available here. This is one of our other websites, CDRC Maps. The paper was available in this journal as open access, so anybody can go and download it. And what actually happened with this is Transport for London picked it up, and they've used it in some of their modelling and are creating a typology of users. And this will end up being used in their planning for sort of capacity issues within the sort of Transport for London sort of travel network. So it's a nice example of an impact case which wouldn't have happened if they hadn't been able to see all of this stuff which was out in the public domain. And the second example, which is another geodemographic classification, but this time for the United States, we built this this classification a couple of years ago. We created, again, this paper here is open access, so anyone can get it. We created an online map using a tool called CartoDB. And actually what happened was this company picked it up. They've actually got a different name now. They're just called Carto. And they used it as a launch product in this new data observatory. So they're interested in pooling data, but just for the entire globe. And they use this as a launch product. So now we've actually had a visit from their head of research, and we're doing other projects with them. So some of our other typologies we've built are now available within their system, because we produce everything in an open way and it's open access. I mean, if they sell services around this, so they put data in their service into their system that they then license to other people, they can access that. Now, from my perspective, this is quite nice. I mean, I don't get any payments for this, but they are willing to tell me who's using it. Now, in terms of these impact cases, that's very, very helpful. So at some point in the next sort of month or so, I'll get a list of all the companies who have subscribed and are using this in some of their own sort of analytics. And then it gives you a route in which you can actually document and evidence that impact. So it might be a company who's increased profits by using this. It could be a social enterprise has generated more money for their charity, for example. So again, this wouldn't have happened if it hadn't been in the sort of open, created openly, which been able to redistribute it and placed in the public domain.